Casey, put it off my microphone. No, wait, my camera. That's the one. And I'm gonna screen. Can you see my screen? See? Okay. Read it. MATLAB, where are you? I assume you can hear me?
Yes, sir.
Okay, very good. We're gonna wait it just to make sure everybody joins. Chris? Data, what's data? Data. Alex, hear me? Well, it disappeared. Alex disappeared. Yes. Your microphone is off. If you acknowledge me, either turn your microphone on and say so, chat me, text me.
Can you hear me?
Yes, Alex, I can hear you.
Okay, sorry, my mic is acting up today,
Um,
so I'm fine.
all right, very good. Just so if your mic goes out, just let me know through chat.
Yeah, thanks. I'm going to now.
Okay, very good. Thank you. Okay, get started. Let me review by just, I'm going to start with neural network. I want to see if I can have some coverage with neural networks today. And I'm going to do some basic principles MATLAB, and from that actually do some demonstration concepts in on a website. So go. One was this, and this is this one. I'm going to so 2 inputs, 2 outputs. Although the number of inputs are now fixed, you can have as many number of inputs. It's not so far-fetched these days to have a neuron that consists of tens of thousands or possibly 100,000 networks inputs. Have inputs x1, x2, and you have output. You will start the whole process by each one of these input certain weight, and you calculate the simplest operation is x1 times u1 x2 times w2. In the case if you have the general essentially equation becomes xi wi I from 1 to n. And it output. And the simplest case, this is a neuron. Now, this particular neuron, you can see that it is producing a continuous number. So it depends on what these this entire summation is going to be. Again, so wi is are numbers that range from anywhere to negative infinity to infinity, theoretically. Positive or negative indicating whether that particular input acts as an excitatory element or inhibitory element. Positive excitatory, negative inhibitory. So, particular neuron that its output that it is continuous in value anywhere again from negative infinity to infinity is appropriate for that prediction. Prediction meaning the output of the neuron goes anywhere again. You're just predicting a number. Like somebody asked in previous lectures, I want to get the shoe size, I want to get a weight, I want to get a height. So this height then is can be any number between 0 and infinity, so you can calculate it this way. So this would be the neuron for prediction. Okay. Now if you go forward, I don't need to go forward, but I need to write anything. So this was one that I actually presented at the end of last class. Neural networks actually become the much of neural network, whether location or it's in its architecture, these neurons that you're interested in, and it performs exactly the same thing as before, with the exception of now it performs a certain nonlinearity. So let me go back and rewrite. So if I was to just re-implement the same thing, x1, w1, x2 with w2, and calculate an output that it is 1 times w1 plus x times w2. There's a button here. Cool. Okay, so pre-level neuron would just calculate this. But neuron that actually has what is called a nonlinearity activation. So it's here activation. I don't have handwriting, it's because I see a much smaller screen here. So the nonlinearity, the simplest form that would adhere to the model logical neuron would be the following. So each neuron is going to have a threshold theta, and I'm going to be activation. And the output of the neuron is then going to be equal to if the one exceeds my threshold, higher. If activation is less than my theta, then I'm going to remain at 0. Unfortunately, a nonlinearity, a very harsh, very discrete nonlinearity, and if you spend knowledge in this field, you'll see that this particular nonlinearity is how neurons kind of operate, but from the mathematical perspective is not differentiable, and that causes certain issues. So this kind of a neuron would be where you have x1 through xn, and this particular information, if it exceeds the value of theta, it fires 1. If it's less than theta, it reduces value to 0. Okay. Now, what I want, this is just a little bit of medical thing that I presented right now. If you don't want to hear it, just stick your fingers in your ears and just go la 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 la. But I'm going to present it anyways. So this, if my output of my if this is what I am interested in looking, I can always look at the following. I can say, how if I just modify everything such that I was 1 to n before, I can say it goes from 1 to n1 such that 1 is always 1. Value of wi is equal to theta. If I reformulate that exact equation that I have up there to the one down here, then nonlinearity will become, the translation becomes 1 if the value is greater than or equal to 0, becomes 0 if it is less than or equal less than 0. Threshold is it in here. The value now has been embedded in the solution in the form of adding theta being the n plus 1. This should be n plus 1. So this is actually have to compare it to a value of theta. You just compare. If it is above 0, you fire. If it is below 0, 0. This is just exactly the same thing. Now, having that, the concept of the network becomes illustrated to a single neuron, but the same principle applies to the larger complex neural networks. In this neuron, we are going to establish a relationship between inputs x1 through xn and the output O. And what to do? We want the network to optimize U1 through Wn and its threshold, such given input produces the output, the desired output, and then processes referred to as training. So the training, your W's are arbitrarily selected. At the end of the training, your W's have been optimized to produce most corrupting between the input and output. Okay, is that simple enough? Is that Alex? Can you let me know if you're okay with this?
Yeah.
Okay. So, Genoa, I see you have two. Are you also okay? Going once, right? Okay, very good. What I want to do from here, I want to switch back to MATLAB. I don't want to focus. So a big challenge in the whole field of artificial neural network going forward is that this is just a single neuron. Now, neurons connect together in a network, which then becomes artificial neural network. So it becomes a collection of neurons. And the big challenge is that how do you train a bigger neural network and network of these neurons and not single neurons? It's kind of like it's pretty much a done deal. But what I want to do is, so I'm skipping over all the training that goes. What training is? Abstract training optimizes your weight of a neural network, and what I just focus on what are the strengths of neural network. How would you use it in MATLAB, and what are the strengths of it? So going forward, I'm going to put this aside. And slideshow. Ooh. Wait, are you okay? It's going to be appearing right. All right. Let me, so what I have here, and I'm happy to actually disclose all of this, and I'll put it as part of the final package that you're going to wrap it up, and I'm going to have it somewhere for you to download. Now, what is a data set and some scripts that I have written in MATLAB that actually train neural net a single neuron to perform the task of logical AND. A logical AND. Okay, so suddenly I realized anything for that one. So let me just start. So this is my input actually put in a variety of places. I have my D is my desired input. I'm sorry, output. Data, or the two of that one. And this is what input is. So if I was, so let me just plot my input. Data set that is kind of supposed to represent digital logic, that I have input in my first dimension that's either 0 or 1, or scattered with a bit of noise. Second input that also scattered is between either 0 or 1, with the noise scattering of the input. So I generated 100 points in each one of these clusters, and the input of the network is to perform logical binary AND operation on this data. familiar with what that logical binary AND operation is 0 and 0. This thing should produce an output of 0. 1 ANDed with 0, that would be this guy, should produce an output of 0. 0 and 1 should be this cluster should be produce an output of 0. So all these three clusters should produce an output of 0. This particular should produce an output of 1. So or one single neuron, I'm going to train it such that it's going to produce an output of 0 for these two, an output of 1 for this one. We start the process by randomly selecting the work. That's some arbitrarily randomly selected. I'm going to perform that. Will generate seeing here 3 red dots indicating classes. Red is the class 0. Green is the class 1. And what you see in this mesh, I'm going to turn around, is the neural network with randomly selected weight does not have a non-linearity that 0 or 1 nonlinearity. If as to introduce the effect of nonlinearity, I just wanted to show you what exactly it does. The following. If it actually, so it would look something like this. Wait, that's a pretty good guess. You know why? Sorry. That's after. So this is really what it should look like for random weight. It will look like this. That it produces output of 0.6, essentially for the entire set of my data. I don't know if this representation is clear to everybody what I'm trying to do. If not, please chime in and let me know if you have questions. This becomes essentially means of illustrating stuff going forward for the next 3 or 4 exercises. So important to stop and make sure that you understand what I'm doing. Alex and you guys,
yeah.
Okay. And January comes and goes. January is here. Okay, very good. So now the whole, if I was to remove, make sure if I was to see on the effect of the nonlinearity where it tries to make fire 0 or not fire, and just make it if it was, this is the same space, bend based on that rule of if you're above 0, then it's 0. If it's below 0, then it produces an output of 0. Anyways, your nonlinearity in there, which basically means this is what I am interested in. So I'm going to go to this confined to nonlinearity being present. And clearly this neural network is not doing a good job of it's seeing the green very nicely, but its output that should for 0 for red is remaining at 0.8, 0.7, and that's not a good thing. So at this, you usually deploy sort of a mechanism where you give it the entire list of stuff, in this particular case, 400 and 400 desired output, and use the network to train itself so that it produces the best mapping between input and output. So in here is a script that I have written, and it produces a W, which I'm going to pass it to my plotting. And all, let me see, was before, and after training, it becomes where now has produced an out near 1 for that class green and near 0 for the class that's red. And the reason that it is not even more distinct between 1 and 0 is because I prematurely have stopped the training processing here. So now I have a neuron that actually can perform the task of binary logical and it was to extend the learning even further. This particular of going from 0 jumping to 1 would become even more clear and distinct. Okay. So, are there any questions? Caleb, Chris. Yeah. This basically, because the network has not been trained, so it's just I randomly selected weights for this network. That means when I go back and ask, based on your current state, how well do you do in discriminating ones from zeros, the input or output? How well does it match the desired output? Right? The question is, what the question? What is this? Yeah. Yeah. So network in the current state that it is, it gave it a value of 0, 0 as input. I would produce 0, whereas right now, so what is above this cluster corresponds to 0, 0. It would correspond approximately up here, which is about 0.8. Yeah, so at 0, 0 would produce an output of approximately what do you see? So it would be here that corresponds to about 0.8. All right, this network is not producing the desired output, or is very erroneous. In fact, the green class gets a classification 1. The output should be 1, it's producing 1. But 3, the output should be 0, it's producing an output of 0.8-ish. Now training, the network becomes this. That for the cluster that should produce an output of 1, it's producing approximately 0.9. And data here that should produce an output of 0 is producing an output less than 0.2. That I'm getting exactly zeros and ones because I stopped the training prematurely. However, theoretically, I will converge to 0 and 1. I will not become exactly 0.1. So if I had extended this transition that goes kind of like this, by the way, this is called sigmoidal nonlinearity because it looks kind of like an S-ish looking thing. So there's a kind of looks like an S. So this transition would be even sharper, such that it would come all the way here, and then from here it would make a very distinct jump up, and it would become a 1. So and that it would then produce the correct, more so the desired output. All right, here everybody. Let me hear from Jean-Noel. Let me hear from Alex. Casey, do you have to add to this? Is everybody okay on this? Okay. And Alex, assume you're okay unless you say so. Say otherwise. Okay. So just a single neuron. The point that I want to bring to your attention, go back to binary decision tree, going back to linear discriminant analysis. Let me see if I find. So let's look at this guy maybe. So this guy. So this is my space, right? And I can ask a question of how would binary decision tree handle this? Would we be able to handle this, yes or no? How would we be able to handle it? That's my first question. The second question is, if I was to perform some sort of a linear discriminant analysis, and linear discriminant analysis would be simply just draw a diagonal line, would it accomplish this task for me or not? So let me hear feedback. First, by decision tree, would it be able to address this problem? would be able to, binary decision tree would draw a line vertical or horizontal, just some fine tune that, but all those, so at this point, what it would do, it would draw a line horizontal at about 0.5 and a vertical at 0.5. And from there would be, if you're below line, you're class 0. If you're line, then if you left, then you are this. If you're to the right, you're this, and it would resolve the issue perfectly fine, right? Okay. So now discriminants. Linear discriminant is one I didn't go over. They are actually in the app. The only, and they are very well studied, mathematically proven that they can give the optimal separation of your space based on linear boundaries. So tools in there, but so I want to view that. So all machine learning techniques, all they do, they come up with their decision boundary. They draw a line through space, and if you're on this side or something, if you're on this side, you're something else. So the question becomes, whether it's linearly separable. That means, can I draw a line in here and say, to separate them, and clearly so, you draw a line right underneath the green that puts red on one side, green on the other side. So linear discriminant analyses could do this too, right? So at this point, those two guys would win. Network seems to be doing fine too. Now, let's go back to the view. This is highlighting the decision values of your neural network based on color values. So yellow represents full 1, very dark blue, navy blue represents a full 0, and anything in between is a gradient between 0 and 1. You guys mean, like, for example, this value of, I don't know, maybe this blue would correspond, and let's look at it. So this some sort of a green would correspond to the value of 0.8. A kind of like middle would be 0.6. The point to illustrate, by looking at this, what would you say the discriminability of neural network? Is it linear or is it non-linear? Is it doing a line separating spaces for you? Is it actually making some sort of a bizarre curvature? Is that apparent, I'm asking? So the answer is completely linear. So basically what it is doing, if you see these various shades of color, one of these corresponds to 0.5. And you can see that if you were to follow any shade, it would be really linear. That's kind of diagonally set. And that's what neural network is doing, has created this guy, such if I was to draw a line on a value of 0.5 would be exactly, if I was to highlight every point on the surface that corresponds to a value of 0.5 would be exactly aligned. And it would be, so 0.5 corresponds to a particular value here, and you can see that all trends go linearly. The pointal neuron performs nothing more amazing than, let's say, linear discriminant. It doesn't do all. Good with that point? So it is essentially equivalent to linear discriminant analysis that draws a line in space, diagonal of any form, bipartitions the space by using that particular line. It's an angry look now. It's not inquisitive look, it's just angry. Discriminant and quadratic? So linear discriminant analysis, I don't think anything to that to do with that entity. It's just a simple way of writing an equation y equals ax plus b, that it divides space into two partitions. When you're on one side of it, you're one thing. When you're on the other side of it, you're something else. And studied one of the most linear discriminant analysis, Fisher discriminant analysis is one of the ones that is very efficient. But the point is, the neuron doesn't do anything. So see if I can demonstrate, find any, Wikipedia. Ultimately, key means nearest neighbor, maybe. If you're interested in this, I don't, discriminant analysis are good for problems that you can just draw a line and separate everything. But would your problem be things like this? How do you use this particular instance? Now you can draw a line that clearly separates solid dots from the filled dots from the ones that actually are empty in the middle. If you really want to effectively do this, you have to do this nonlinear discrimination of the space. And the is neural network does this. And the how, but I will stop until you guys ask me that question. The nature of the question, is it clear or not? So a single neuron, my argument is, does this, but somehow a network of these neurons can actually perform create boundaries similar to this one. Clear what the claim is with neural network, and because it can arbitrarily draw these complex boundaries, then it can solve complex problems. And that's kind of appeal of neural network. I don't know how much there is. I think I'm just going to quickly show the neural network tool in MATLAB. And from there, I'm going to really much something else. So if you go on that app thing, and if you do your classification or just do neural network versions of here, you can do pattern recognition, time series, clustering, neural network thing. You can go pattern recognition. In here, it walks you through. So if you have your data, you're good. If you don't have your own data, go forward. In here, you can clear what should be your input, which in this is where's my input. What should be your output, your desired output that your training network to make is that one. And it will ask you some examples. If you have data to play around with, you can do that here. Otherwise, you load the example data. And there are enough examples in here that you can just click on it and say import, just automatically here. And with all will be filled in. So which one? What is it? So the color is rose. And once you're, this is begin to, so some of the concepts from the very beginning lecture is that you need to break your data into training, testing, and validation set becomes you can control that here. For validation, by the way, you can read up a little bit more to see what it says. And once in place, you have this issue of what should be the architecture of your network. So your inputs, in this particular case, I have 3 inputs, still should have been 2. I just create third input because of reason. Then you have the hidden layer and output layer. You design the architecture of your neural network. I'm going to come back to this a little bit. And once you have designed the architecture of your neural network, and then when you proceed forward, yeah, why is it not word? Take this one for it to create, and then you in your neural network. This particular instance, this is a very trivial problem to solve. It will give you what it did. You can look at confusion matrix. Yeah. Here, this matrix pretty much doing 100% success in. So this is the training set. And this is the set is pretty much as very, very successful too. So clearly it's performing this task. So pick for example, the training confusion matrix. Yeah, it was all one. It was all one because of a reason. It was useless. It was. Okay. Uh, the training testing neural network can be something as simple as this in lab, and there are a variety of approaches you take. The components that you want to as an architect, a neural network is this. There are actually two parts. There's more part, depending on how expert you are and at what level you want to delve into redesigning your architecture. What I call this, the very first place that you want to actually look at is this. How many would this is 10? Why is it not 2? You can select retrain. Network basically does just as well. So there it is. Just as well, but 2 neurons. And the question is, why 2, why 10, why not just even go back? So if I was to say, give me 1 hidden neuron. Train it. Caleb, did it come up? Third one, perfectly fine. This is a problem that is a fairly trivial problem to solve. In fact, a full-blown neural network is an overkill. But if your problem requires a little bit more customization, you can go through the command line to actually architect designing your neural network. You can train it, you can test it, and once it is tested, you can deploy. Network is very scalable compared to, remember, there was that k-nearest neighbor that it was just a hog for, in computation complexity. That's a neural network, and then a demo. So I want to, I just basically what happens. Artificial neural networks. So architecture, everybody has adopted, with the exception of the deep neural network and all the models, let's just say up to about 1990s, the general architecture that everybody agreed on is the following. So you have this is called the input. You will have is called the hidden layer, and then you have this is called your output layer. And traditionally, 3 layers is what everybody agreed on. Excuse me. 3 layers uses. 3 layers is computationally shown theoretically to be complete, and it can create kind of a complex landscape. I'm not sure what that means. Layer, layer, hidden layer, output layer. Do you feel a question here? I'm going to continue. Comes in. So input. X1 goes in your input. X2 goes in your input. X3 on it, or input here. This is your output of your network. You may have 1 output, or you may have M outputs. So have a neural network, for example, that performs compression, where you give it 1,000 pieces of information, and you want it to condense it into same thing. This kind of a neural network. You may have a network that receives input, generates logical and um, or a variety of logical operations. So you may have multiple outputs. So how many hidden layers? So the traditional neural network, the shallow neural network, if I was to call it, would have only a single hidden layer. The difference is show neural network and what is currently to be deep neural network is any architecture that has one hidden layer is essentially considered to be a deep neural network, deep learning neural network. So if you have multiple hidden layers, then you essentially are working with a deep neural network. So in neural networks, in the theory of computational neural network, having a single layer on a very wide one is computationally complete. You can always your neural network grow by having a narrow but many number of hidden layers, or have it to be short, to be shallow, meaning only this exact one single hidden layer, but be very, very deep, being very wide, meaning having many hidden neurons. That answers your question. Would neurons perform no particular function other than receiving the input and then casting it to all the hidden layers? So the connectivity would be with the course associated out here. So we connect neuron I to opposite to hidden neuron J. And hidden neuron, the same thing. It connects. It performs its function as we discussed. It receives the input from whatever is coming into it, multiplied by corresponding weights, add all up, and depending on the activation level, it either goes through some sort of a activation function, either has an output value of 1 or 0, and then those all propagate to the output, and output performs its multiplication. I'm going to call these weights to be ij, that connects hidden neuron I to output neuron j, that performs the same thing. Whatever is coming to output number 1, multiplies it by corresponding weight, adds them all up, compares it to some threshold value, and fires or now fires based on decisioning criteria. This is what the neural network consists of. And it is happening. The first layer doesn't do anything except that broadcasts information. Every single one of these neurons is drawn in space. Every single one of neurons is bisecting the space based on its own weights, divides into section above, section below one. The outbound takes the bisections of the hidden neurons and from there assembles it together so that creates essentially a piecewise estimate of that nonlinear function. And here I'm going to just jump into demonstration and show you something that might be of benefit. You're not going to give me all my bookmarks? TensorFlow? Which one? Yeah, this is the one. So this full tool to actually look at when it comes to understanding what neural networks are doing. So in case, I'll start with something like this. So the data I'm going to use, this is on the left-hand side, you have all the available data for your study. So this data set, like our example one, that's very clearly separable. And network, you can design the architecture, first decide on how many number of hidden layers you want. And then for hidden layer, you can decide how many neurons you want to add to that hidden layer. So for this particular instance, what I'm going to do, I'm going to have two inputs. You have hidden neuron, and this is the output of my output neuron. Don't worry about it. It's just something got to do with how fast you learn. This is the nonlinearity that you can deploy. There are a variety of them. Linear would just essentially turn it into a prediction algorithm. Sigmoid and RELU are three commonly used ones, although these days everybody uses RELU. I'm going to do sigmoid for now, just to illustrate the point. Don't worry about regularization. You're performing classification, not regression. If you were performing regression, this particular would actually, your out neurons would no longer have nonlinearity. It would just calculate the number and throw it out there. Epoch is the number of iterations that your system is engaged in the training. So I'm going to start, actually, before starting, the initial weights of the system actually show you how the network is currently. If I float over each one of the neurons, it shows you, illustrates to you how the neuron is performing its discrimination, how it is actually separating the space. At this point, this particular neuron, you can see that going diagonal with a positive lobe, and essentially that is how it's going across like this, and that's how it's making its classification. The random weight. I begin to train the network, and the output of the network right now is really discriminating any one of them. It's like the background is just the same color. So the corner of the system drops, and you can see that sigmoidal that it is drawing a threshold in space would be this light, white light, and blue would indicate one class, brown would indicate the class. This is what the output neuron is doing. Hidden neuron is performing a similar thing, but as you can see, it has one line, and the output neuron essentially receives the input of the hidden layer. There, it additionally performs some. It can establish consensus. In this case, the separation is very simple. So to be illustrated here, if you select it to be more complex, such as this one, this is similar to approximately, this is actually an exclusive OR problem. So if I start training the network with one neuron, the output of the network would be, as you can see that the general performance is dropping. But in here, you can see that by just drawing a simple line, you cannot separate all of these four from each other. The neuron is doing, and the output neuron, the only thing that can do is essentially echo that. But if I would increase my number of neurons, hidden neurons, you can see it is beginning to exhibit more nonlinear behavior in its discrimination. It's no longer just straight lines that it is drawing, but it is actually more complex landscape. If you use the number of hidden neurons even more, you can see it actually beginning to the nonlinearity ability of the neural network becomes clear. Now, if you look at this carefully, you will see that this boundary that has been established here, this highly nonlinear boundary, is actually a linear combination of individual hidden neurons. So if I was to look at individual hidden neuron, is dissecting the bottom left corner. this one actually kind of isolating the top right corner. This one isolating the remainder, so you can look at it as either the really dark blue or dark white. So it's the top left corner. And the hidden, what the output layer does, it just takes these concepts of separation across these three entities, which then arrives at such a complex landscape. The problem is that the network is drawing very complex boundaries in space and performing far more complex tasks than any of the other ones that we saw. The challenge work is coming up, so this particular instance is very easy to pictorially look at it and see what it is doing and come up with the right number of neurons. Now, I could have increased the number of hidden in here. By in the number of hidden layers, the system complexity increases. For some reason, my output, I guess, is coming. You can see the separation boundaries are gradually become nonlinear. And it just plays that it does very nice separation of those states, very complex. So the neural network is to have plenty of training sets, which these days that's not a problem. On the architect's perspective is to design an architecture that fits the problem. There are no general rules that people apply, and the best thing to do is then to be minimalist, to start with the smallest network that seems to do the trick, and from there expand the complexity of the network, adding additional hidden layers and additional hidden neurons. So probably reduce this and do it again. Curious to know if it actually works. Doesn't seem like it's going. Let me actually, while I'm here, let me copy paste this particular URL tab maybe. Or if you found with this thing. So neural network on Python, they're available in R, they're available in MATLAB, they're available in C++. Language you can think of pretty much has got a neural network. Data, tinker around with it, architecture, whether you should have one single layer, multiple layers, how many neurons, what should be the attributes of neurons, should that have nonlinearity. So all of those become the reason why a person who knows this field is in hand would make good money. There's essentially a lot of things to wrap your brain around. Yeah. Right. So basically, x1 this dimension. You can see it is orange, positive is blue. X1, x2 is the vertical dimension is blue, orange. First doesn't do anything. That's why they're clearly just separated positive, negative. The second, is just doing something. Anything. Let me just increase this. So let me make sure everybody's okay. So who has survived? So do you have any questions? Is there anything I can do to help? Feel free to contact me in the future if you have any questions related to these. But for now, I have any questions? Okay. At point, over the weekend, I can convert these things to something reasonable and load them onto YouTube. So at some point soon, hopefully by next week, all of these should be loaded on there. Everyone, see you later. Bye, Casey. It says recording.